Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 8, Applications of Integration, and today we're talking about topic 8.2, which is connecting position, velocity, and acceleration of functions using integrals. Enjoy today's notes. All right, welcome to 8.2, which is connecting position, velocity, and acceleration with integrals. One of the things we want to be thinking about as we're entering this lesson is that we know that position, velocity, acceleration, if we're thinking about it, it is the main physics application. So it's the main physics application for AP Calculus. And if you're thinking back, we've talked a little bit about position, velocity, acceleration already this year. Specifically, it came up back in section 4.2 when we were talking about this with respect to derivatives. And now we're flipping the page and talking a little bit about it with integrals for this. One of the things I want to talk about right off the bat is a little bit of some knowledge. We want to make sure that we still remember and in terms of the connections between position, velocity, and acceleration. Specifically, back in Unit 2, we talked about the fact that in order to get from a position function, which frequently is referred to as s of t, velocity is v of t, and acceleration is, of course, a of t. In order to get from that position to velocity, we know that we can take a derivative to get from the position function to the velocity function. And to get from velocity to acceleration, we can also take a derivative with respect to x or with respect to time, depending upon what our function is. I suppose these are with respect to time, so we would want our derivative with respect to time. Since this relationship is true with going in terms of derivatives, we can actually work in the opposite direction with respect to antiderivatives, aka integrals in this case. So if I have an acceleration function and I want to get back to velocity, I can take the integral with respect to time to get from that acceleration to velocity, and to go again from velocity to position, I can take that integral with respect to time as well. This means that, of course, position is the second antiderivative of acceleration, while we know that acceleration is the second derivative of position. This relationship works in both ways, which is useful for us as we're thinking about this and going into today's lesson. Let's jump into some examples here. We've got problem number 1, which says a particle moves along the x-axis with an acceleration of a of t is equal to 12t minus 4. The particle's velocity is 18 centimeters per second at t equals 2. So the velocity is 18 centimeters per second at t equals 2, and the initial position of the particle is 8 centimeters. What is a function x of t that represents the position of the particle? I'm going to definitely need some space here, so I'm going to split this up into two little areas in order to show my work. We know that the acceleration a of t is equal to 12t minus 4, and in order for me to get the position, we're going to need to go from the acceleration to the velocity first, and then from the velocity to the position afterwards. So to get from that acceleration to the velocity, I'm going to take the antiderivative of this, or the integral of this. And specifically, I'm going to say that the velocity is going to be equal to the integral of this 12t minus 4 with respect to time, dt for this. In this case, we know from our work in chapter 6 that to evaluate this indefinite integral here, that we can take the antiderivative of each of these terms. That means that my velocity here is going to be equal to essentially our reverse power rule. We're going to need to add 1 to the exponent and then divide by that new exponent. And then for our next term, we're going to do the same thing. There is no t, so we're going to end up with a t to the 1, and then we're going to divide by that, and by that exponent of 1. And then since we are finding an antiderivative, an indefinite integral here, we are going to need a constant of integration, plus c, when we take that antiderivative here. In order for us to be able to move forward, though, I do want to find that plus c that we've got. And in order to find that, we're going to use essentially the initial information they gave us. They told us that the particle's velocity is 18 centimeters per second at t equals 2. So this is going to allow me here to solve for that c value for the velocity function. And in order to do that, first I'm going to maybe simplify some of the information that we've got here. We've got that v of t is going to be equal to that 12 divided by 2 is going to give me 6t squared. And then I've got, looks like minus 4t plus whatever my c is for this velocity function. If we plug in our t equals 2, again, using that initial condition that we've got right here, that when t equals 2, the velocity is 18, I can set this equal to my velocity, which is 18, and that's going to be equal to 6 times 2 squared minus 4 times 2 plus whatever the c value is for this. And so we get 18 is equal to, what's that? Looks like 24 minus 8 plus our c. And so if we subtract that, that looks like it's going to be, I'll continue over here. This looks like it's going to be 18 is equal to 16 plus the c, which would mean that c would need to be equal to 2 for that equation for the velocity function for this. So with that said, I'm going to move over here to the next part. We just said that the velocity equation, the velocity function, is going to be equal to 6t squared minus 4t, and we said plus the c that we've got, but we found out that that c was 2, so I am going to put a 2 in that spot and continue working from there. Now we've got our velocity function. We just found it. But again, the goal in this problem is we're trying to find the position function. And again, going back to our roadmap here, if we've got velocity, in order to get the position, we're going to need to take an integral or an antiderivative. So I will do that yet again, a second time in this problem in order to do that. And if we do that, we are going to get our x of t. That position function is going to be equal to the integral of our velocity, which is that 6t squared minus 4t plus 2 with respect to time for that. If we take an antiderivative, doing that reverse power rule, we're going to end up with that 6t, and then adding 1 to that exponent is going to become a 3. We divide by that new exponent, which is 3 there. We then have our minus 4t, and again, if we increase that exponent by 1, that's going to become a squared, and then we divide by that new exponent. And then we've got our plus 2 t to the 1 over 1. And again, we're going to need a constant because we found that antiderivative. Now, this is a different constant. It is technically a different plus c than the one over here. This was our c for the velocity function that we had over here, while this is our c for the position function. And yet again, though, I'm going to try to find this, because we want the position of the particle, I do need to know what the c is for this particular problem. And in this case, I'm going to use the other information they gave me, which is that the initial position of the particle is 8 centimeters. If we're talking about the initial position, if we're thinking about that information here, that is specifically going to be when t is equal to 0. That's going to be the initial position. So when t equals 0, it looks like that position is 8 centimeters, and we're going to use that once we simplify our equation here. So let's do that. If we simplify, this looks like that my x of t is going to be equal to 6 divided by 3 is going to be 2t to the third, minus that 4 divided by 2, which is 2t squared, plus the 2t plus my c. And again, when t equals 0, that position is 8. So let's plug in that information here. That looks like we've got 8 is going to be equal to 2 times that 0 cubed minus 2 times our 0 squared plus 2 times our 0 plus whatever c is. This looks like it's going to be 0. We've got 0, we've got 0, which means that our 8 is going to be equal to that c value for this problem. And they again asked us what is the function that represents the position of the particle. So to finalize this problem, I want to put my final answer, maybe I'll put it in a box here, that x of t, that position function, is going to be my 2t cubed minus my 2t squared plus my 2t, and we said plus c, and we just found out that that c was 8, so I'm going to put a plus 8 here on the end. And that is going to be my position function that represents this situation where we've got an acceleration of 12t minus 4 and our given information up here in problem number 1. But that's going to be our answer for number 1. Let's take a look at number 2. Number 2 says Mr. Brust is driving across town to Mr. Sullivan's house to play with a new set of Star Wars figures. Mr. Brust's speed would obviously vary throughout the drive, but because he's so cool, he came up with a function that represents his velocity in miles per minute at any time t in minutes since he left his house during the 30-minute drive. They ask us to set up the expressions for the following scenarios and then use a calculator to solve. Looks like the velocity function that we're using here for this problem is this sine of 0.3t plus the natural log of t plus 1 minus 2. And it looks like they also have a graph of that function over here, which is sort of nice, going between t equals 0 and t equals 30. So if we're setting up the expressions for the following scenarios with that calculator, we're going to be able to, of course, use our fn_int feature, which we talked about back in chapter 6, in order to help us find this. If we want to find how far Mr. Brust is from his house after 10 minutes, since this is a velocity function, the distance is going to be coming from the change in position over that time. And so if we're thinking about, we were given a velocity function in this problem, to get back to that position and that change in position here, we are going to need to integrate that velocity function in order to do that. And so we can represent this by finding the integral from 0 to 10, since it's over that 10 minutes, of the velocity function that they gave us, specifically this one that I've got highlighted here in green, in order to find that. And if we find that integral using our technology, this is going to be equal to 3.010 miles, is that distance that Mr. Brust is from his house after 10 minutes. And again, that's coming from integrating that velocity function to find that change in position from t equals 0 to t equals 10. How far is Mr. Brust from his house after 15 minutes? Same idea. Because we were given a velocity function, we want to integrate to find that change in position. So that is going to be the integral from 0 to 15 of that velocity function. And again, putting that into our technology or our graphing calculator, that's going to give me 3.397 miles as that change in position over that 15 minutes. So he's a little bit further than where he was after 10 minutes. So you can see sort of the distance between the t equals 10 to t equals 15 for that particular problem. Part C, if Mr. Brust arrives at Mr. Sullivan's house after 30 minutes, how far away does he live? Well, if he arrives there after 30 minutes, that means he was realistically traveling for that full 30 minutes, and we would need to find that integral similar to Part A and Part B from 0 to the 30 minutes that he was traveling for that velocity function that they gave us. In this particular case, if we use our technology, this is going to end up being 22.824 miles, which definitely looks like he traveled a significant distance between that t equals 15 and t equals 30, going from that 3.397 to the 22.824 miles for this. For Part D, how many miles did Mr. Brust drive? The thing that makes this a little bit more challenging is thinking about it is possible that, maybe he did not drive directly to Mr. Sullivan's house. Maybe that there is like some positive direction and negative direction. And so just thinking about this, the challenge is that there can be movement, like there can be essentially positive velocity, so going in the positive direction, and then also negative velocity, which would be going in that negative direction. And we do notice for this equation this equation in this graph that's up here, that there are times, because this is a velocity function, v of t, that it looks like that he has a negative velocity, which means he's moving in the negative direction or away from Mr. Sullivan's house. Between, looks like these two times, and then also between these two times, he has some negative velocity, so he's moving away away from the house, while when the velocity is positive, he's moving in the direction of Mr. Sullivan's house for this. Because we want to think about the total miles that he drove, that's going to take into account both the velocity, the positive velocity, and the negative velocity. In general, we want to make that negative velocity positive, and so a trick that we can actually do here is to bring in the absolute value. If we want to think about how many miles that he went in total, instead of integrating the velocity from 0 to 30 like we did in part C, we can find the integral of the absolute value of the velocity function. So the integral of the absolute value of that velocity function with respect to time. And I do want to emphasize for this, again, these are absolute value symbols, right? So absolute value symbols for that equation. And what that's going to do is it's going to count both the positive velocity and the negative velocity in total, and that's going to give us the total distance traveled for this. If we, again, use our technology in order to evaluate this with that absolute value, this is going to tell us that Mr. Brust traveled 28.497 miles. And so clearly some of that was in the negative direction because he had a negative velocity, but in total, he traveled 28.497 miles of distance in order to go 22.824 miles of where that house is, right? So some of that was maybe going back towards the house and double backing because of, could be roads, all sorts of things it could be for this. So big takeaway here. If we integrate the velocity, that's going to be slightly different than if we integrate the absolute value of the velocity. If we integrate the velocity, this is going to give us essentially displacement, right? Like how far away or how far does this object end up from where it started after that time. While if we integrate the absolute value of the velocity, right, if we're thinking about those absolute value symbols for this, this is going to give us something slightly different, which is the total distance traveled. And again, those are slightly different. Sometimes you want the displacement, sometimes you want the total distance traveled. The only difference in this case is whether it has the absolute value versus if it doesn't. We don't want to get this confused with just the absolute value of velocity, right? We're without the integral symbol for this. This is something we talked about back in chapter 2, but velocity is speed with a direction. And so because velocity can be positive or negative, if you take the absolute value of velocity, that is going to simply give you the speed of the object at that particular point. And that is, again, if we don't have an integral symbol, that is just going to give us speed. Let's take a look at problem number 3. A particle's velocity is given by v of t is equal to 4t cubed minus 6t squared plus 1. The function x of t represents the position of the particle along the x-axis. They want us to find the position of the particle after 3 seconds if x of 0 is equal to 5 for this. And then eventually for part B, finding the position of the particle after 2 seconds if x of 1 is equal to negative 2. In general, I think maybe I'm going to write this up here. Problems that are like this are using something that we've talked about called the fundamental theorem of calculus, which I will highlight and just sort of remind us that the FTC, the fundamental theorem of calculus, was this thing that said that the integral from a to b of some f prime of x dx is equal to f of b minus f of a. You might remember that this is the rule that allowed us to essentially evaluate a definite integral by taking an antiderivative and then plugging in those limits of integration and then subtracting. We can use this equation to our advantage in problems like this, and I'm going to refer to the way that we're going to use it as what's called FTC with a twist. So FTC with a twist. And what's the twist? Literally what I'm going to do is I'm going to take the minus f of a, and I'm going to essentially add it to the other side of this equation, which means that if we're going to do that, then I'm going to have this equation which is f of a plus this integral from a to b of f prime of x dx is equal to f of b. Now this comes up in these particular problems with position, velocity, acceleration, because the f of a is essentially our initial position. This is our initial position. And if we add to it this integral of, I guess, technically the velocity in this particular problem, essentially what this piece is going to give us is the displacement, right? If we take the integral of the velocity function, if we take the initial position, we add the displacement, that is going to end up giving us the final position. So the final position. So that is just generally pretty useful. If we take your initial position and you add the integral of the velocity, which is the displacement, that's going to give you the final position after a certain period of time. So let's use that in this particular problem. Problem number 3, with that particle's velocity that's given to us here in this equation, we know that x of t is the position of the particle along the x-axis. If we find the position of the particle after 3 seconds, if the initial position is 5, thinking about this equation here, my f of a, that initial position is going to be the 5 that we've got. And to find the displacement, we're going to need to integrate the velocity over that same time period, going from, looks like, my t equals 0 to t equals 3. So that's going to be the integral from 0 to 3. 0 to 3 of that velocity function that we've got, which is that 4t cubed minus my 6t squared plus 1 with respect to my time. And then if we add that initial position to that displacement, that's going to give us our final position, which in this case is going to be whatever x of 3 is, the position when x equals 3. We, of course, can integrate this a couple of different ways, but since we're using calculators at least earlier in this lesson, I'm going to integrate this using my calculator in order to do that. In general here, I'll just mention, of course, we can take an antiderivative here and then use our FTC like up here in order to evaluate by taking an antiderivative and then plugging in those limits of integration and subtracting. But altogether, if you do find that integral, it's going to end up being 30 for this particular problem. And if we do 5 plus that 30, that's going to give me 35, which is our position at t equals 3. And so that is going to be our answer for part A. For part B, they want us to find the position of the particle after 2 seconds if x of 1 is equal to -2. Same idea. This is essentially my initial position for this particular problem, even though it's when t equals 1. That position here looks like it's -2, and we're going to need to integrate the displacement going from the 2 time values that they gave me. So going from t equals 1 to t equals 2, that's going to be from 1 to 2 for the same velocity equation that we've got here, which is that 4t cubed minus 6t squared plus 1 with respect to time. And again, if we needed to do this by hand, we absolutely could, but given that we're using technology in this lesson, I'm going to integrate using that. This particular one, if we find that integral, is going to end up being our -2 that we have here plus 2, and if we do that, this is going to be equal to the position at t equals 2, so x of 2 for that. It looks like that's going to be -2 plus 2 is going to be 0, so x of 2, the position, is going to be 0 at t equals 2 for that particular problem. Last one here. We've got problem number 4, which is what is the total distance traveled by a particle during the first 4 seconds if the particle's velocity function is given by v of t is equal to -15t plus 3. Show the setup and your work. Just in general here, we know for this particular problem that we can find the total distance traveled by using this equation here, the integral of the absolute value of the velocity function. So I'm going to use that to my advantage for this, and that is going to be the integral from 0 to 4, because they want the first 4 seconds, so that's from 0 to 4, of that absolute value, which I'll highlight. It's the absolute value of my velocity, which is that -15t plus 3. With respect to time for that. In general here, we can integrate that again if we have access to a calculator. Great. If we do that, I'll just mention that this particular answer for this problem is equal to 6 if we do that. However, We actually have a graph of the velocity function over here. And so if we're thinking about this, and if for some reason we didn't have access to a calculator, we could use that velocity graph in order to think about it. The integral from 0 to 4 of this velocity function, of course, is going to be the area between the curve and the x-axis from 0 to 4. So here is t equals 0. Here is t equals 4. That area between the curve and the x-axis is going to be this piece right here and this piece right here, which technically, if we're thinking about this, is going to be the integral from 0 to 2 of that velocity function of v of t dt, plus the integral from 2 to 4 of that v of t dt. Now, since we are trying to find the total distance traveled for this, we do want this absolute value to carry for both of these. So it would be the absolute value of this integral from 0 to 2 of v of t dt and the absolute value of this integral from 2 to 4 of v of t dt. Taking a look over here at the actual function, we see that we've got a triangle that has a height of 3 and a base of 2. So if we think about the area of that triangle, it's going to be 1/2 times 3 times 2, which is going to be 3 units for that. That is already positive, so it's going to stay positive because of that absolute value. Over here, we see that this triangle is below the x-axis, so that area is technically negative. And when we find that area, it's going to be 1/2 times 2 times 3. So that is going to be 1/2 times 2 times 3, which is going to give me 3 for that. But because of this absolute value, that area of that -3 that we've got down here is going to become positive, making this a positive 3. And again, we can see that 3 plus 3 is giving us 6, which we can confirm with our result from our calculator earlier on. So in general, if I've got a calculator, of course I'm going to try to use that to use my fnint feature on my calculator or on Desmos. Otherwise, I can use the graph of the velocity function to help me out if I don't want to find antiderivatives for this. But otherwise, that is going to be our notes for today for this 8.2. We've got some practice. In general, we know the way that we get better at math is through practice and through learning from our mistakes. So I encourage you to take advantage of that. Good luck as you're working through these, and have a great rest of your day.